Hello, my name is Andreas Zegowitz and I'm the manager of the group called Thermal Properties and Artificial Climate Simulation at the Fraunhofer Institute for Building Physics IBP in Germany. In this lecture, based on the Lighthouse project in AGARTALA, you will learn about the energy efficiency enhancement measurements for the light gauge steel structural system and pre-engineered steel structured system. I will show you how to enhance the energy and efficiency by giving you some background information about the energy efficiency itself, and especially in the module we will look at the influence of internal gains. I will go deeper into the energy demand balancing and in the end discuss steps to reduce the energy demand in this special construction. The first step will be about the basics of the energy efficiency of buildings. What does balancing of thermal gains mean and what effect has it on the efficiency? The balancing between the total annual thermal gains and losses can be described in building physics by means of the following overall equation, which we had already seen frequently. On the left side are the sources. These are all sources that bring a thermal gain. And on the right side are all the things that cause thermal losses. The equation works exactly when the sum of all gains equals the sum of all losses. I will explain in a moment why I have put the QC value here in brackets. Let's take a look at the individual values. On the source side of the equation we have the thermal energy gain from the sun Qs, which comes mainly through the windows. There is also the heating demand QH, which is balanced by the heating and can be controlled best. The internal heat gain QI are mainly caused by humans and by waste heat from electronic devices in the household. The things are described by the ventilation heat losses HV, which mainly occur at the windows or through mechanical ventilation. And in addition, the transmission heat losses HT are on the thermal loss side, which occur on all external surfaces of the buildings. The QC value describes the cooling demand on the loss side. This becomes relevant when the gains on the left-hand side become too high, that the things on the right-hand side, such as HV or HT, can not longer fulfill the equation. You can certainly imagine that this is, of course, only a mathematical quantity. In order to initially fulfill the equation in this case, it first makes sense to reduce the artificially generated value QH. Only when the solar inputs and internal heat gains are still too high, the cooling demand arises in order to balance it. Of course, this is theoretically and considered for short periods of time, but in real application you will sometimes find a simultaneous heating and cooling demand over the year, which has to do with the changing climatic conditions over the year. Now let's take a look at the values calculated for the respective sources and sinks in the basic version of your building in AGARTALA. The background on the individual values are already been explained in the other modules. Each value is related to 1 year. The solar energy inputs in the equation amount to 2093 kilowatt hour. How these are calculated was already described in the last modules 5.3. The internal energy gains amounts to 730 kilowatt hour, which were already discussed in module 2.3. The heating demand amounts to 86 kilowatt hour, the cooling demand to minus 2303 kilowatt hour, which was already explained in module 2.3. Here you can see now exactly the special feature that I discussed earlier. In our example, there is both a heating and a cooling demand. This is due to the calculation for 1 year, so that there were apparently some days in which the left side did not lead to a balanced result and, in theory, a heating demand arose. However, this is also very low compared to the cooling demand. On the right side of the equation, e.g. the sinks, the values are negative. The ventilation heat sink is minus 606 kilowatt hours, which was discussed in 4.3. The transmission heat sinks are minus 94 kilowatt hour, which I hope you remember from 3.3, where the calculation of this value was explained. Here you can see now again in the diagram the ratios of the respective parts of the balancing equation. It can be seen that the majority of the balancing equation on the source side of the thermal energy arises from the solar thermal inputs, which in return must be balanced on the sink side by the cooling. With this background knowledge, we can now look at the possibilities to increase the energy efficiency with the AGARTALA LHP. Which measures lead to a reduction in the overall balance? In the balancing equation, the cooling demand is the value with which the equation is balanced. If the energy input on the source side is too high, the transmission heat losses and ventilation heat losses are no longer sufficient to reach zero. The dwelling therefore heats up. The heat demand is exactly the opposite. If too little energy is entered in the balance sheet, a heat demand arises that can be responded to, for example, by a heating system. Let us therefore look at various scenarios that have been simulated, always in relation to our base case scenario. First, we look at the change in cooling and heating demand with interior insulation. We see that insulation does not fundamentally lead to a particularly increased cooling demand. Only the heating demand is slightly increased by the increased insulation and the resulting reduced energy inputs. Only the internal loads and the increase of these leads to a significant increase of the resulting cooling demand. Respectively, the heating demand is reduced. However, if these internal loads are reduced or omitted, and the incoming solar radiation is additionally blocked by shading, the cooling demand is significantly reduced. Now let's look at scenarios with external insulation. With external insulation, the cooling demand is reduced because the wall is not heated up. Exterior insulation also has a positive effect on the heating requirement. It significantly reduces the requirement at the variant with purely exterior insulation and the variant with internal loads. If there are internal loads with external insulation, these are again decisive with regard to the cooling demand, as the heat is generated inside and kept inside. However, a variant with external insulation and additional shading leads to the highest heating energy demand of the variants considered, as the sun rays can no longer penetrate the flat and thus the source side is reduced. So let's wrap up this module in a conclusion. We see that most of the cooling demand comes from the source of the internal loads, so most of the energy is needed by meeting this resulting cooling demand. Furthermore, the combination of insulation in conjunction with shadowing offers the greatest potential for energy reduction, especially that of reducing cooling energy. On the one hand side, by reducing solar gains, and on the other hand, by being able to control the heat loss. And when that, I would like to end the video and thank you for your attention until the next video, with which will be about durability optimization. Goodbye, thank you.